All right, so hopefully everyone feels pretty confident in their ability to carry out some stoichiometric calculations. So in this video, I'm going to talk to you about limiting reactants. And I alluded to this in the last video. We have made numerous assumptions thus far. And I want to go through those so everyone knows that there are some things that occur during these reactions that may not always give you what theoretically you should have, okay? So first and foremost, we're assuming that all reactions go to completion and that the reactants are completely consumed. That is not always the case. In fact, you have heard me say excess reactant. You've seen that in several of the problems. You've seen that on the problem sets. Well, now I'm going to give you the background to fully understand why that distinction is so important. All right. Also, we're assuming no side reactions are occurring during the reaction. So a side reaction or an alternate reaction is a reaction that occurs during the main reaction. Okay, it occurs to a lesser extent, but it does occur. And when it occurs, it leads to an overall decrease in the amount of product predicted through stoichiometry. Okay, reactants are pure. In fact, in Stoichiometry podcast 4, I'm going to talk to you a little bit about percentage composition and percentage purity. So reactants are just 100% pure. And that reactants are consumed in the exact molar ratios as predicted from a balanced chemical equation, those molar ratios that we've been hammering out the last couple podcasts, all right? So I want to go back to this PHET simulation example that I discussed in Stoic Podcast 1. And let's take a look at our sandwich again. Remember this 2 to 1 to 1 to 1 ratio. I need those 2 slices of bread, 1 slice of meat, 1 slice of cheese to make 1 delicious sandwich. All right, so look at this example here. Okay, now we have 4 slices of bread and 2 meats and 2 cheese. We can make 2 sandwiches, okay? 4 to 2 to 2 to 2 ratios means we can have twice the product. All right, now let's look at this final example here. We have 4 pieces of bread, 4 pieces of meat, but only 2 pieces of cheese. And we have 6 pieces of bread in this example here. All right. Okay. So anyways, 6 pieces of bread, 4 pieces of meat, 2 pieces of cheese. How many sandwiches can I produce? I need a complete sandwich composed of 2 pieces of bread, 1 piece of meat, 1 piece of cheese. So I make my first sandwich, I make my second sandwich, and I go to make my third, but I cannot. The reason for this is I am limited. I'm run out of cheese. I cannot make more sandwiches. I am done. I can only make 2 because cheese is the limiting reactant in this example. Okay, so I'm going to have some excess reagents or reactants. I'm going to have leftover meat. Okay, all the limiting reactant, i.e. the cheese, is gone, but I'm going to have 2 pieces of bread and 2 pieces of meat that are in excess. Okay, so let's get a couple definitions down here. Formal definitions for limiting reactant, and you may hear this referred to as limiting reagent, is the reactant that's completely consumed, like the cheese was in our example. All right, this species limits the amount of product. The cheese limited the amount of sandwiches. We could only make 2. We had excess reagents or reactants, which are the reactants that remain once all the limiting reactants are used up. They're the leftovers. So they're the leftover pieces of meat. They're the leftover pieces of bread in this example. Okay? All right. So let's get into some calculations. These are even more fun. You guys are going to absolutely love these. So what volume of hydrogen gas, measured at STP, is produced when 8 grams of lithium metal are reacted with 10 grams of water? What mass of excess reactant remains once the reaction is completed? Okay, pause the podcast, go ahead and write this out, balance it, then unpause it, and we'll continue on. All right, so solid lithium into the water. We get our lithium hydroxide, which is aqueous. You actually did a net ionic equation for this back in the chemical reactions unit. And then the evolution of hydrogen gas as a result. So we're going to get this one. Let's lay it out here. So 10 grams of water. Where are we at? 10.0 grams of water are produced when 8 grams. Now, do you notice something's different here? You don't see, you're not being told explicitly which one is an excess. And you're being given 2 of the reactants, all right? So that is critical. You need to be able to recognize these problems, and I should have, I'll write them. Okay, so 8 grams, 10 grams, and you're given both reactants here. And you're asked something about the product, be it grams, be it molecules, be it, in this case, liters. All right, so you are going to use stoichiometry to find out which one of these reactants is limiting and which one of these is in excess. In order to do that, you're going to do a gram to liter conversion here and a gram to liter conversion here. All right. Whichever one gives the smaller value, that reactant is your limiting reactant. Okay, so again, we're going to do stoichiometry, gram to liter stoich for one reactant, gram to liter stoich for the other. And the key to recognizing these problems always, if you're not told which one's in excess, you have to do some additional computations to determine which one is limiting, because you will not create more product than what the limiting reactant allows to occur. All right. Land of the mole, here we go. Okay, so grams, we're going to use molar mass. And guys, we're doing this 2 times, 1 for each reactant. Then we'll get moles of one reactant, use the molar ratio to convert us into the product. And then from the product at STP, we're going to determine the liters of gas. The smallest answer is the one that we choose as a limiting reactant to move forward with. Okay, so give this a shot on your own. You have the values for each reactant. You should have 2 lines of dimensional analysis and stoichiometry going on here. Okay, first one, grams of lithium, molar mass of lithium gives me the moles as we discussed on the mole map. Here's the molar ratio we've talked about extensively, and it is a 1 to 2. Okay, there's a 1 there, and you guys know that. So that gets me into my hydrogen Brinkelhoff gas, and 1 mole of hydrogen gas will occupy at STP 22.4 liters. Boom, boom, plug and chug, multiply everything on the top, divide that quantity by everything on the bottom, and with 2 sig figs, I get 13 liters. We're not done. Now let's move on to our other reactant and do the same exact thing, except this time with 10 grams of water. And as we go through, using our plan that we devised using the map, the mole map, mole ratio. It's a 1 to 2. So I'm going to go ahead and 1 mole and 1 to 2. There you go. And 1 mole at STP of any gas will occupy 22.4 liters. Multiply everything on top, divide by bottom. Bam, there you go. So I ask you, which reactant is limiting? And if you said the water, then you are correct. The water is the limiting reactant, okay? And all 10 grams, we're going to say, are consumed. And there's leftover. That's like all the cheese being consumed, and there's meat and bread left over. Use stoichiometry. Now we're going to convert the limiting, okay? So we've answered this part of it, okay? Which is what volume of gas? What's our answer? This. We're not going to produce any more than we're limited. So that's the answer. And sometimes these problems will be just presented in that way. Well, how much of the product is produced? And they won't say or allude to the fact. You need to know you were given both reactants or however many, and you need to use Stoich to find out which one is limiting, because you're not going to make any more. We're not going to make 13 liters. 6.22 liters is the correct answer. All right. But this question, and that's why I love this unit, goes on and says, what mass of the excess remains? Okay. So it's basically, we know some of this is left over, but how much? How much actually is left over? So in order to find that, we need to find out how much is consumed. Okay. We know all the water is consumed. Okay. But we want to know how much of the lithium is consumed, because we know how much lithium we started with. We started with 8 grams of lithium. Okay. So we need some additional stoichiometric calculations here. We're going to convert the limiting reactant into the excess reactant. So we're going to convert the limiting into question mark grams of lithium. All right, so here we go. We had 10 here, and our calculation, we get to use a lot of the same numbers, except this time it's a 2 to 2 mole ratio, okay? And as I've said before, you can say, well, for every 2, there's 2. That's fine, but for now, humor me and include this. Show this work in your computation, and it'll help you not get confused. So now we have moles of lithium, 2 moles of lithium, and 1 mole of lithium. We use the molar mass, and that's going to convert us to the unit we want, which is mass. And that is the amount of lithium consumed. This problem doesn't say how much was consumed. It says how much is left over, i.e. excess remains, how much remains. So in order to do that, let me carry this all over so we can look at this from a kind of a clean perspective. There's a lot going on there. So same information here, and we ended with that much being consumed. And I've already alluded to the fact, hey guys, we started with 8 grams. 3.85 were consumed in the reaction and converted into product. All the water was consumed, but we have leftover lithium. So intuitively, we will subtract 3.85 grams from the 8 grams. And our answer to the final part of this question is 4.2 grams of the lithium remain unconsumed, unreacted. They're still there. They are not reacting any longer. Okay? All right. Example number 2. So an acid spill containing 12 grams of pure sulfuric acid. So we're assuming purity here. 100% pure sulfuric acid is neutralized by 80.0 grams of sodium bicarbonate or sodium hydrogen carbonate or baking soda. What volume of water is formed. This is different. What mass of excess? Okay, so that's what we were asked in the last one, just applying it to a different chemical reaction. And then you're given the density to help you make a connection here. All right. So you may recall the podcast on molar volume and density. So if you do, there's a connection here. We can use the density, the mass over volume of the water to actually find out how much liquid water is formed in this case. So in our dimensional analysis, we will incorporate this somehow, some way. And as I've alluded to in class and in previous videos, we are big picture, and we will constantly be looping content so you remember why you learned something and how it can be applied to something new. In this case, applying density to a stoichiometry limiting reactant problem. So let's go ahead and look at the ostensibly, okay, this is a double replacement reaction. All right, this is a metathesis reaction. However, carbonic acid will spontaneously, and we just talked about this in the last video, decompose into water and carbon dioxide. All right, and if you've ever done this, I mean, we have a whole series of labs coming up. But just even as a kid, I used to take baking soda and vinegar, okay, which is a dilute acetic acid, and mix them. And I know that it bubbled, and I know there was some gas that was giving off, and it often overflowed the container. All right, so that's similar here. You have this type of acid reaction occurring, and we're forming an aqueous product with really a bunch of spectators going on there, evolving this carbon dioxide gas and also forming liquid water. We are balanced. We have a 1 to 2 to 1 to 2 to 2 mole ratio. Now let's get down to the stoichiometry here. We are given an acid containing so much sulfuric, and it's neutralized. So we are given both reactants. So anytime we're given both reactants, 12 grams here, and we have 80 grams here, this should scream limiting reactant problem. I need to use stoichiometry to convert both of them to the desired product. All right, in this case here, question mark, milliliters, liters, whatever unit we end up with in the end, that doesn't matter. But it's that volume of a liquid and the connection density. Okay, so let's look at what this would be like with our dimensional analysis here. So grams on top, grams on bottom. I'm multiplying, I'm at the mole, moles of sulfuric acid for every 2 mole. That's that stoichiometric ratio, and you guys know that by this point. Where'd it go? There it is. Okay, so you guys know that by this point. And then in 1 mole of water, there's 18.02 grams of water, and for every 1 milliliter of water, there's 1 gram of water. All right, and we've already explored that in lab as well. So the answer here with 3 significant figures is that we're going to form 4.41 milliliters of water. And again, whether you convert it into liters or not, that's up to you. But our conversion factor here was given in grams per mil. And so we are all set, and that is our answer, but we're not done yet. We're not done yet. We have to go through all of this again. And with our 80 grams of sodium bicarbonate, we flip through. I'm going to go quick, because you guys are getting too good at this. You already know all this stuff. All right, so we're going to take our, our computation here, and you end with 17.16 mils. So what's our answer? Well, I already alluded to that by underlining it and saying that's the answer, is 4.41 milliliters of water. That is our limiting reactant. So sulfuric is our limiting reactant. Sometimes I'll label it with an LR. And our sodium bicarbonate is our excess reactant or reagent. All right. So this is wrong because we are limited. It's like running out of cheese. So let's go and find the second part. What mass is left over? Now I want you to think about the process that you're going to use. What are you going to do? Well, you're going to take your limiting reactant, remember, and you're going to convert it into your excess reactant. That's going to give you how much of the excess reactant is used or consumed. Then you're going to subtract that quantity from the amount in the problem. All right. So in this case, 80 grams minus something. And that's going to tell you how much excess remains unreacted. All right, so let's see what that's going to look like here. Converting, in this case here, our limiting into the excess. I am using the arrow there, and we have our usual stuff going on here, and the molar mass of sodium bicarbonate, and we're trying to find the mass of sodium bicarbonate. We have a number here, and that is how much is consumed. So the last step, 80 minus 20.6 is going to give us our answer of 59.4 grams of excess sodium bicarbonate remains. All right, so that's how you do limiting reactant problems. They're going to give you both reactants, ask you something about the product. We've already started to explore this in lab. As I've already mentioned, we're going to investigate these concepts in lab through some limiting reactant experiments involving acetic acid and sodium bicarbonate. That's where we're at, and we're just starting to have fun, and I'll see you guys in class.